Okay, thanks very much, Alex. Okay, so the title is Developing and Selecting Tribological Coatings, or The Road to Nowhere. The reason why I've subtitled it The Road to Nowhere, a couple of reasons actually. The first one is if we think about the move between research through to products, involves an array of people: engineers, physicists, material scientists, metallurgists, statisticians, theoreticians, chemists, chemical engineers, etc. And it needs all of those people to travel along this road to reach the solutions for the actual end-use applications, which can be very varied in their anti-wear requirements. So within ICAM, we do have access to all that range of skills and abilities and knowledge. So that's the first analogy for the road to nowhere. So the talk is going to begin with an explanation of some historical background to tribology, which is the study of friction and wear, or rubbing surfaces to be precise. And I'm going to talk about the importance of hardness and elastic modulus and their ratio, the importance of resilience and toughness in coatings and surfaces, and then the requirements of different tribological contacts, and then the benefits of nanocomposite and nanolayered and glassy metal coatings to solve the problems which we identify, and then finish off with something about what we call duplex systems, and then some final comments. If we think about the history of tribology, a colleague of mine, Kenneth Holmberg, was the first to point out that we tend to study tribology in different length scales, and then later we put that on a time base, and we realized that before the Industrial Revolution, people were interested in large machinery on the meter and decimeter scale, looking at efficiency and reliability and lifetime. And then as we went along, we started to look at things at the decimeter and down to the several millimeter scale, started to look at torques and forces and vibrations, clearances and alignments, etc. And then Hertz came along with his contact theories of elastic contacts, and he was able to look at things like the contact pressure and pitting and scuffing. Then around about 1950 was probably the birth of what we regard as tribology in its modern sense, and that really began with the group in Cambridge, Bowden and Tabor, and other groups around the world. And they started to look at fracture, elastic and plastic contact of asperities and deformation, debris creation and surface layers, etc. And then I guess you could say that in this present century, we've entered the age of nanotribology, which has enabled us to really understand better what's gone before. We now have the tools and the techniques to have a better understanding of tribology. So you could say that we started looking at the macro scale, we looked at large machines, started to look at the macro scale. Now we look at things like material transfer, tribochemical changes, micromechanical changes, cracks and fracture, and now start to look at interactions on the atomic scale. However, if we go back to the 1950s and the Cambridge group, there was a desire to try to develop a kind of unified theory of tribology and try to see if there were straightforward equations which could describe wear. And for example, many of them came up with the idea that wear is equal to a constant times load over hardness. That's what is generally regarded as Archard's law. Regrettably, I guess, that turns out to be incorrect. And there are other properties that are as important as hardness. And a gentleman, in fact, called O'Beirle recognized this in the early 50s, but his work was ignored. So O'Beirle was at the Caterpillar Company, and he published a paper which said that the elastic modulus can also have an important role in defining wear resistance. And he came along in the 1950s with a paper, and as I say, tribologists probably realised that Archer's law was oversimplistic, but in a way it led many people to put too much emphasis on hardness, a consideration that hardness was the main requirement that they had from coatings. So it's taken some time to reverse that overemphasis on hardness. This is Obel's paper from the Journal of Metals in 1951, in which he pointed out the importance of elastic modulus. So he actually defined something that he called the Model factor, Brinell hardness divided by elastic modulus, and he found that wear decreases with increasing Model value, that it decreases with decreasing elastic modulus for materials with similar hardness, but it actually increases with increasing hardness if the increase in hardness is associated with an increase in elastic modulus. And he found this by doing lots of tests and then ranking materials, and this is an extract from one of his papers, where he got a better correlation between wear and Model factor than he did between wear and hardness and wear and elastic modulus. And of course we can put that onto more consistent units now. We can define elastic modulus in gigapascals, and we can define hardness in gigapascals as well. And what we find is that materials with a good wear resistance tend to have a H/E ratio of around about 0.1 or higher. As you can see here, rubber is very high, but that's a special material, and obviously we can't make engine components out of rubber, but we can use rubber for other things like tyres. But our aim in coatings development is to try to develop coatings with a H/E greater than 0.1. It's a good objective to have. We shouldn't be surprised that H/E is important. We know that, for example, that hard ceramics are wear resistant, they have a high hardness, and elastomers, like rubber, are wear resistant because they have a low elastic modulus. These materials are wear resistant because they're difficult to deform plastically, these because they are easy to deform but they spring back. So it's, in a way, it's understandable that a combination of those properties might give us a good indication of wear resistance. So although Obel was the first to identify the ratio of hardness to elastic modulus as an excellent ranking parameter for wear resistance, it turns out that bearing designers have known it for many decades, and they use something called the plasticity index when deciding the mechanical properties and the surface finish needed on bearings. So they use this plasticity index, which you'll notice has an E/H ratio in it, and it also has another factor related to surface roughness. So the bearing designers really thought that they had little control over this parameter, and therefore if they wanted to prevent a rough surface from exhibiting any plastic deformation, then they'd have to polish it to a very high level to avoid any plastic deformation of asperities. So in textbooks you see this kind of thing, where it shows you that in order to ensure that a surface remains elastic and the asperities don't plastically deform, you have to polish them right down to a very high finish. Now we can actually get a low plasticity index just by controlling the elastic modulus and the hardness. So that index was originally developed for uncoated surfaces, and the consideration of the elastic modulus to hardness ratio is even more important for coatings. That's because the E/H ratio defines the elastic strain to yield. That's the amount of strain a coating can take before yielding, and therefore its ability to deflect in sympathy with the substrate. So you know that if you take the stress strain curve, the slope of the stress strain curve is the elastic modulus. So E is equal to Y over the strain. In this case, the limiting yield stress is Y, and the limiting strain at the point of yield is epsilon F. So E is equal to Y over epsilon F. So epsilon F is equal to Y over E. So since Y is directly related to hardness, typically hardness is 3 times yield stress for most surfaces. You can see, therefore, that the elastic strain to yield is directly related to the ratio of hardness to the modulus. So that's one reason why H over E is important for coating. So if you take a very simplistic view of this, if you had a coating which maybe had, this is just representational, it's not an exact scale diagram, but if you had a coating which happened to be slightly softer than another coating that had a lower elastic modulus, then it could have a longer elastic strength to yield and therefore would protect the underlying material for longer, at a higher rate of strain, higher level of strain. So in this particular representation, this coating could protect this material even when this material is strained beyond its yield point, which obviously would be an excellent property for a coating to have if it continues to provide protection to the surface even when the underlying surface has yielded. There's another reason why the H over E ratio is important. It's because it provides an indication of something that we call the elastic resilience of a surface. That's its ability to absorb energy elastically. So if you take a simple tensile test as an illustration, you pull this tensile test piece up to a maximum load of P and an extension of X. The energy which is absorbed elastically in that is the area under that curve. In a way, if you think of it simply, it's the average force times the distance moved is the work you put in. So the energy absorbed is that area, half P times X. Now, because that energy, if you like, is half Px, and we know that sigma is P over A, force over area, and epsilon, the strain, is equal to the extension over the length, you can actually transpose this, and it turns out that the energy absorbed is half sigma squared over 2E times the volume. The energy absorbed per unit volume is sigma times epsilon. And that's the elastic resilience, which is a well-known parameter. And again, since the sigma is directly related, the maximum sigma is related to the hardness, that we see here that the ability to absorb energy elastically is related to H squared over E. So again, another reason why the H over E ratio is important. Further work on modelling of surfaces was done by a real guru of elastic contacts. That was Ken Johnson in Cambridge. And Ken Johnson literally wrote the book on the subject, and he modelled a hemispherical indenter against a surface, and he showed that the force that you required to yield a surface was given by this expression. Again, you see here there's H cubed over E squared, so it tells us again that H over E is important. This is basically related to the fact that an elastic surface can spread the load more, and therefore you have to apply a greater load in order to make it yield if the surface is more elastic, has a lower elastic modulus. So that's where that particular formula comes from. Some people think this is a purer form of H over E. In fact, it's not. It's specific to a hemispherical indenter against a surface. There are also reasons of fracture mechanics also. I won't go into it, but those of you who are familiar with fracture mechanics will know that work by Griffiths and Irwin, etc., define a critical stress for crack propagation, sigma c, defined by this expression, and Gc is termed as strain energy release rate, and it's a measure of fracture toughness. And you can see here that Gc is sigma c squared pi a over E. So again, we see from fracture mechanics considerations that H squared over E also gives an indication of the ability of a surface to prevent fracture. So yet another H over E ratio, which leads us to the belief that the ratio of hardness and modulus are important in defining the wear resistance of the surface. We can go further than this, and we can say that H over E indicates the surface ability to absorb energy and recover elastically, and it's particularly important in impact loading situations. If you think about it further, the actual ability to absorb impact will actually be defined by not only the elastic range, but also the plastic range of the material. And a guy called Smart said that for cavitation, which is one particular kind of impact, what we should think about is not y squared over 2e or h squared over 2e, but the UTS squared over 2e. And that's in recognition of the UTS being reached in the plastic state, and therefore some ability to absorb energy can occur plastically. I mean, you should think about the toughness being defined by the total area under the stress strain curve, not just the elastic part, the elastic resilience. So we know, for example, that a mild steel, a structural steel, is tougher than, for example, a high carbon spring steel. This might have a higher elastic resilience, but this is tougher. This is more able to absorb impact. So now what we're getting into is that it could even be a good thing for a tribological surface to have some ductility. And that would go really right against the thoughts of thinking of those early tribology theorists. There's also an argument around toughness for polymers. Another guru of the subject, John Lancaster, did a lot of studies, and he's one of the leading lights, or was one of the leading lights, sadly passed away in 2014. John looked at the wear of polymers and found that those giving the lowest wear rate were the ones with the highest toughness. Is actually reciprocal of toughness here. So the ones with the highest toughness are the ones here giving the lowest wear rate. So again, there's a toughness argument even for polymers, which holds true. Again, this sigma u, epsilon u comes into this consideration. So to reduce wear, the key is to design the coating with appropriate combination of mechanical and chemical properties to meet the needs of the application. And these mechanical properties can include hardness, elasticity, and perhaps surprisingly ductility, especially if the coating needs to be able to absorb impact energy or accommodate substrate deformations. So if a coating contains a ductile constituent, it can be tougher. An illustration of how the combination of low and high modulus phases can be beneficial in a coating would be a multi-layered coating with a hard, soft layered structure. And such a coating can deflect under load without fracture, since the softer, lower modulus layers absorb the shear deformation. So if you consider this as a thick coating, and you load it, and the substrate deforms, the coating could crack. If, however, you have a thick coating which has layers of hard, soft, or high modulus, low modulus is another way to think of it, and you load it, then it won't crack because the hard layers are thinner, so they don't see such a high bending stress because they're thinner, and they're allowed to deform because the shear takes place in the soft, low modulus layers. If you think of a book, a paperback book, and you bend it, it will obviously bend. Even though it's wood, really, if it was a block of wood, it would break. Because the layers can slide over each other, they don't break, and each layer is thin, so it doesn't see a high bending stress. Those of you who studied stress analysis will recall that the maximum stress increases with distance from the neutral axis. So from a thick section, you get a high bending stress. For these thin sections, you get lower bending stresses and an ability to accommodate deformation. So this just shows how hard, soft, how the shear takes place in the softer layer. But this is just meant to represent how it's better to combine properties in a coating, to combine hardness and ductility and elasticity in order to get the optimum response to loading. So how can we achieve that obviously desirable combination of hardness, elasticity and ductility? And one answer is by using nanocomposite or nanolayered coatings. Now this is the other area where the road to nowhere comes in, because even the Romans knew that the best way to create a wear-resistant surface was to have hard blocks in there, separated by a compliant, if you like, grain boundary phase, which can accommodate the deformation. So as the chariots rode over this road, if that was a solid piece of stone, it would just break up and fail. Whereas with this kind of construction, if you like, a cobbled road construction, it can accommodate the loading and the deformations without failure. So this is where we take that analogy of the road to nowhere a step further, and we use this to help us to this concept to help us to design nanocomposite coatings. There's an illustration here of a real-life multi-layer coating. This is a multi-layer titanium nitride coating. Titanium nitride coatings typically spoil off at about 10 microns thick due to buildup of stress. But by having this kind of thick coating in a multi-layer, it survives and it accommodates deformation very well without debonding. And those kinds of coatings are now used on compressor blades, especially where they're used in sandy, abrasive environments. And this information is courtesy of Warwick, Cambridge, Take Back. So a perfect example there of a real-life coating which would fail if it wasn't for the fact that it combined hardness and ductility and an ability to absorb impact energy. So why, that's a layered structure, but why are nanocomposites even better? Well, a number of reasons. One with nanocomposites is we can get so-called hole pitch hardening. We can get grain size induced hardening. We can retain the elastic modulus of the metallic species in that composite. And there is a further benefit, and that is that the corrosion rates are more uniform. Intergranular corrosion is suppressed, and so degradation is more uniform and predictable. We don't get localized pitting corrosion. So overall, with a nanocomposite, we get the an enhancement of H over E, and we get good corrosion resistance and better wear resistance overall. One of the earliest proponents of nanocomposite coatings was a guy called Musil in the Czech Republic, Jindřich Musil. And he originally said that the idea would be to have a metal nitride in, for example, an amorphous soft metal grain boundary phase. And our approach is to go slightly further than this. What we're looking at is nitrogen or boron interstitially hardened metal crystallites within a soft metal matrix to try to retain that metallic characteristic in terms of ensuring a low modulus phase, but still getting hardened effect due to the interstitial hardening within the grain. And this shows a typical example of such a coating. This is a chromium with nitrogen interstitial hardening in a copper grain boundary phase. And these coatings are remarkable because they're basically metallic, but they have ceramic-like hardness levels, but metallic-like elastic moduli. And they can accommodate deformation, obviously going to perform very well in a tribological situation because of their ability to absorb and accommodate deformation while still being quite hard. So how does a nanocomposite coating be beneficial in tribological contacts? So what I want to try to explain here is that the requirements of different types of contacts are many and varied, and they aren't just hardness. So we can't just believe Archard's equation. We can't just assume that we need hardness to get appropriate reductions in wear. So we look here at 7 typical types of contact, and I'm just going to go through each one and explain what we're looking for from each of these types of contacts in terms of the properties of the coating and the underlying substrate. So for example, if you have a simple contact stress, a static contact stress, you need load support, you need adequate strength within the coating, adequate hardness, and you need sufficient toughness. So toughness is clearly important. You don't want cracking to occur. For a sliding contact, you probably need low friction. You need sufficient adhesive strength between the coating and the substrate, and you need adequate cohesive strength within the coating and within the substrate as well. And you need sufficient elasticity in the coating to deform with the substrate without fracture. For a fatigue situation, normally you need good surface finish, you need a crack arresting capability, you need adequate hardness and toughness as well. So although hardness comes into many of these requirements, it isn't by no means the only requirement that they have. If you think about fretting, that's a low amplitude, very low amplitude fatigue type situation. You often need low friction, again sufficient hardness, but there's still a lot of discussion over the relative importance of hardness and ductility in fretting contacts, and you need good surface finish. In abrasion, that's probably the mechanism where you really do need hardness. Many studies have shown that typically to resist abrasion by a hard abrasive particle or a hard counterface, then your surface should be at least 30% higher in hardness than the abradant. So for sure we need hardness, but we also need toughness. We need adequate thickness of the coating so that any abradant doesn't penetrate through the coating. And then you need load support underneath the coating, again, to prevent that abradant penetration through the coating. Another of those types of contact which I illustrated was impact. Requirements for impact resistance are definitely toughness, ability to absorb energy. So you need elasticity and you need deformability, you need good adhesion of the coating to the substrate, and you need cohesive strength both within the coating and within the substrate. And then the final schematic that I showed of a type of contact and the contact situation was when you have chemical dissolution or corrosion. In that situation, you will need a pore-free structure, or you'd ideally like to have a pore-free structure, and you're going to need either a completely chemically inert barrier, or you're going to need some suitable galvanic properties within the coating. So again, we saw that many of these nanocomposite coatings give a dense, relatively pore-free structure. So requirements for wear-resistant coatings are clearly complex and depend on the type of contact. But the other point to make about all of this is that all of those contact types could occur together. Remarkably, they could, and they could occur differently, to different extents, during the life of a component. So any coating that you develop or apply should ideally be adaptive to changing contact conditions. And sometimes we call these chameleon coatings or adaptive coatings. So that's a further requirement, and it has been found that the nanocomposite coatings do provide the possibility to add in this adaptability to the coating. So I would say that most tribological testing has historically tried to model just one type of contact, such as a unidirectional sliding contact, like a pin on disc. And much theory, you might say, including ArcChards, is based on rather unrepresentative types of contact. For example, little attention has been given to repetitive impact contacts. I mean, we've looked at this, we've developed impact testers, and we've looked at the behavior that you get with different coatings under impact conditions. So this is a pneumatically operated impacting machine, and the sample would be here, and that would be an impacting, maybe a tungsten carbide ball hitting the surface at high frequency. And then we look at the nature of the failure under the impact area. And you can get cracking in the indent region, you can get build-up around the indent, you can get cracking around the indent, depending on the coating and the different properties of the substrate and the coating. Now next are some example performance using that impact tester going back some time now. Don't worry about what the coatings were, but just consider the hardnesses. They were all roughly 3 microns thick. Some of them were over 4,700 Vickers Knoop hardness, actually, in this case, and some of them were relatively soft. These were the titanium carbide diamond-like carbon coatings. And what you find in that impact test is the coatings that gave the best impact resistance, the lowest impact volumes, are the more elastic, less hard coatings. And this is really brought out best when you look at the indents after 1,000 impacts, 10,000 impacts, 50,000 impacts. The very hard coating, it looks like it survived, but it hasn't. It's spalled away in this region. Another hard coating has cracked around the periphery, but that titanium DLC mix has survived completely after 50,000 impacts. It looks like there's a slight crack here, but in fact the coating remains bonded and attached to the surface. So that's one example of a coating that's or a test rather, that's shown that coatings with a high hardness to modulus ratio do perform very well. Some people thought that the titanium boron nitrogen system should give good performance because it has a grain size hardening effect in this region here, and can reach hardnesses of over 50 gigapascals in this region. And a lot of work was done on this, trying to look at different places on this, trying to get to different levels of elastic modulus. But one of the issues with it was if you went to somewhere on that diagram to reduce the modulus, the hardness reduced too much. And what was found is it was useful to add aluminium to the system in order to reduce the modulus but still retain a high hardness. And sure enough, as you might expect, when wear tests were done on these, it was those which had the highest ratio of hardness to modulus which performed best in those tests. So that confirmed that coatings must provide adequate hardness with the degree of elasticity and toughness needed for the application. And the above example was for a ceramic, or the previous example was for a ceramic nanocomposite. But as I've said, there's now increasing evidence that metal-based materials offer advantages to those with a high ceramic content. So, for example, a relatively soft nitrogen-doped chromium coating can provide better performance than a harder chromium nitride coating in impact tests. Also, carbon-doped tungsten films have been shown to give better performance than single-phase tungsten carbide coatings in abrasive contact conditions. So just to illustrate this, if we've got a chrome coating and we add nitrogen, we go through and we look at the hardness. The hardness increases as we interstitially harden. Then we put more nitrogen in, we get more of the ceramic phase, more Cr2n and CRN. And then if we then do an impact test on these, the coating that performs best is the relatively soft but elastic interstitially hardened chrome rather than the very hard chrome nitride. Okay. We can also look at, as I mentioned, carbon in tungsten, and for this we looked at the ASTM standard rubber wheel abrasion test. This is the rubber wheel. It's the standard ASTM rubber wheel abrasion test where you allow abradant to pass between the rubber wheel and the test sample. It's an excellent test actually to simulate abrasive wear. And we looked at some carbon-doped tungsten, so it's added carbon to tungsten as the hardness increased and you form the ceramic phase. But down here, relatively hard but not as hard as the full ceramic phase. And guess what? In the abrasion test, the rubber with abrasion test, the coatings that performed best weren't the hard ones. And this really goes against even the theories that were devised for abrasion wear. It was the ones that were slightly less hard but were more elastic that survived best in that rather arduous rubber wheel abrasion test. So we can see that these metallic-based coatings can perform very well. So what design consideration should there be for these nanostructured and even amorphous coatings? Well, I've already mentioned the excellent work done by Musil, and one of his contemporaries at the time was a guy called Stan Vepcek, who was at Munich University at the time. Now, Stan's main aim was to get super hard ceramic nanocomposites. So he set his stall out to get very, very hard coatings using a ceramic approach. So he used a metal nitride nanocomposite in an amorphous silicon nitride matrix and achieved very, very high hardnesses. And that was always his aim. We kind of moved from that and looked at titanium aluminium with nitrogen additions in an amorphous boron nitride matrix in order to get hard but yet relatively elastic nanocomposite coatings. And it's good that we can use sputter deposition techniques and electron beam techniques to do, in a way, combinatorial studies on the effects of different compositions of these materials. And in a single run, you can get a variety of compositions and look at the behavior of those different compositions in nanocomposite coatings. So this is some work that Klaus Rebholz did and has continued to do. This just, actually, I wanted to mention this because many people will say, what's the point of having a metallic nanocomposite because it won't be temperature stable. But actually, we've proved that some of these metallic nanocomposites are remarkably temperature stable. And this is just some work that was done showing the hardness and the elasticity stability even up at 900. And that work was stopped at 900 because of the risk of getting into diffusion with the steel substrate. So many of our preconceptions about metallic nanocomposite proved to be unfounded, and they do seem to have much better performance even under extreme conditions than you might expect. And this is just to show you that there are many of these nitride forming nanocomposites that we've got to go out yet. This is from an extract from a chapter that from a paper that Adrian Leyland and I did, and from a chapter in a book that we wrote. And there are many theses to be written yet, I think, around the concept of metallic nanocomposites and a whole range of nitride forming metals and a whole range of non-nitride formers that we can look at in order to get the optimum mechanical and even chemical properties in these mechanical and mechanically enhanced nanocomposite coatings. One aspect to consider is that this is looking at the amount of soft phase that you need. And this depends on the grain size. So this is the chrome grain size coming down from 10 down to 1 nanometer. And you can see that as you reduce the grain size, in order to have a complete coverage of the grain, you have to go to very high copper content. So there are limits. And if you go to too small a grain, you run the risk of getting grain rotation and no longer getting a hardening effect in these. So there is an optimization to be done on these metal nanocomposite coatings. So this is just showing that for a 2 nanometer grain you need more than 20% copper. So mostly you'd be working in the maybe 5 to 10 nanometer grain size, and typically copper contents of 5 atomic percent and around there, slightly higher. So that leads us on to yet another class, which I class together with the nanocomposites, and that's the glassy metals, which follow some of the same arguments that we've made for metallic nanocomposites. The glassy metals, also many of them, they have high yield strength, low modulus, better corrosion resistance, better fatigue resistance, even than nanocomposites. Sometimes oxidation resistance could be questionable, and their ductility can be questionable, but there are certainly again many glassy metals for us to research. As I said, that according to our theories of hardness and elastic modulus, these materials should give us good wear resistance. Those of you who are unfamiliar with glassy metals, the person who developed the theory for glassy metals, I won't read through this, but Hugh Mothery was the chap that we can thank for the different theories, but it's all to do with the mutual solubility of atoms in the metal alloy, and it's generally restricted when the difference in atomic radii is more than 40% or more, and they don't, if they're large or they're small, they don't tend to mix with average size crystallites or atoms, I should say. So even notionally very similar metals with a high relative mutual solubility can be expected to experience a degree of lattice distortion on the nanoscale when alloyed. and also atoms of a similar size with incomplete valence electron configurations prefer to adopt different crystal structures and tend to exhibit a wide miscibility gap when alloyed in a solid state, thus providing scope for the development of metal nanocomposites and also the metallic glasses, the whole of this theory. So an example of metallic glass would be vitralloy, which is zirconium, titanium, copper, nickel, beryllium. Many of these materials tend to have a high H/E. So I said there's a lot to be done, lots of PhD theses to be written around the area of nanocomposite, metallic nanocomposites and glassy metal nanocomposites. This is just some results from some of our work, and I think I've not got time to go into them in detail, but this shows the amount of copper. This range here, which shows that we're getting good wear resistance for copper contents between about 3 and 20% in this particular case of a chrome copper nitrogen, but just a word of caution, big difference between the 3% and the 3.3% copper here, which in wear resistance. So obviously much research still to be done to optimize the copper content, and you could say the same of the this was one particular glassy metal that we looked at, chrome, titanium, copper, boron, nitrogen, which actually tended to show that it isn't just the hardness and the modulus in this case that controls the wear performance and the chemical nature and the chemical interaction. So there's much to be done to study further the glassy metals and to optimize them for particular types of contacts. And yet again, with these glassy metals, one of the characteristics which can be useful is that they can harden with increasing temperature. I don't know if annealing is the right word, but they can harden with elevated temperatures. So again, very, very interesting properties within the glassy metals. And there are other functionalities in some of these nanostructured coatings. For example, this is a zirconium nitrogen silver coating, some work from Samir Awadi, who looked at these materials, and these promise elevated temperature lubrication, possibly antibacterial properties. Many people have looked at the antibacterial benefits of silver additions in nanocomposites, not least ourselves, and others have looked at the elevated temperature, looking at this adaptability concept, the chameleon concept for coatings, and changing the properties at higher temperature or under different types of environments. In fact, I found this diagram from NASA where they're looking at some copper-based alloys. This is a copper chromium niobium with pretty remarkable high temperature properties. You just wouldn't expect some metallic-based materials like this to offer excellent performance at high temperature, but they really do. And this is a precipitation hardening alloy which gives excellent performance, again, in this kind of series of systems. Many papers now out there on things like chrome copper films, and this is a situation where this particular coating is offering excellent protection at high temperature at 650 degrees C in terms of weight reduction in weight gain. And the results so far with our chrome copper nitrogen and chrome titanium copper boron nitride have shown that these nanocomposite and glassy metal coatings provide very effective protection in both erosion and high temperature oxidation situations, extreme environment conditions, if you like, sometimes due to the capability to form a protective chromium layer on the surface. And other people are interested in super high coatings, super elastic coatings, shape memory materials, nickel, titanium. Some people say that these will offer good performance. Many people, again including ourselves, are looking at these with alloying additions, including niobium and copper. Still looking at the effect of the material in the heat generated in the sliding contact. I just wanted to mention quickly Ali Erdmeyer's work, which is not really related to our work on wear, but he looks at these materials from the tribological effect. And again, he looks at the nanocomposite from toughness point of view, but also from the interaction effect in lubricated contacts. He looks at something that he calls the ionic potential, which is the cationic charge and divided by the radius of the cation, and he talks about how this can enhance the this parameter, ionic potential, can enhance the performance in a lubricant. And he says that the higher the ionic potential, the lower the friction coefficient. These materials have increasing ionic potential and reducing friction. And just to say that one of the materials he looks at is molybdenum nitrogen with copper, and you can see a very dense structure. So I just thought it was interesting that he looks at it from a friction perspective, but we look at it from a work perspective, but these materials still seem to be very promising. And you can see here increasing ionic potential and the best performance from that particular material here. Ionic potential increasing. And he explains it in terms of the effect on the Strybeck curve that this material can have. I'm sure, again, there's more work to be done in that area. So another class of nanocomposite coatings are those based on DLC. I've not mentioned those, but probably the most successful commercial nanocomposite coatings are based on diamond-like carbon. This is a typical nanocomposite DLC coating from Balzers. These are used now very widely on injector systems. This shows part of an injector part. And the reason why these are so beneficial, if you look at the pressures that are being used now on common rail diesel engines, we're now up at something like 29,400 psi. So 1,000 times the pressure in your car tyre, if you like, something like that, is the pressure being used within these injector systems. So you can imagine that those parts are expanding and contracting hugely, and that further emphasizes the need for a long elastic strain to yield so that the coating can absorb that deformation and spring back without failure. Very important. Those coatings are used in all kinds of things. Gears, as an example, where you wouldn't think they would work, but they expand the damage-free region for all these kinds of wear mechanisms and failure mechanisms. And this shows a typical gear and the effect that the coating, nanocomposite coating or nano-lead coating, can have on the fatigue life, on the fatigue limit, the stress that can be applied without any fatigue occurring. So these very thin coatings, maybe only 3 microns thick, can protect these gears under very arduous contact fatigue situations. So nowadays, many things that we use, razor blades, car engine injectors, even the hard disk on your computer has a nanocomposite coating on it. These tend to be chrome nitrogen based. I'm sure they developed them without even thinking about H over E, but it turns out that those particular coatings have a very high H over E, very elastic but hard. We have other requirements from coatings. We need a supporting layer under some coatings. We'd like to allow the use of these lightweight materials, such as aluminium, magnesium, titanium, which can sometimes not offer support to coatings. So we need to apply what we call duplex technology. We need to harden the surface and then coat on top of it. We call that a duplex treatment. And this is an example of a plasma nitriding performed to a titanium part and then coated. This is a Formula One wheel hub, only possible by pre-nitriding before coating, otherwise the coating would just fall off. Many people talk about load support, but they don't define what they mean. But load support is an ability to avoid these different types of failure mechanisms due to deformation, like cracking of the coating debonding, substrate elastic deformation, substrate plastic deformation, substrate fracture, or ploughing friction due to the deformation. So you need a hardening effect underneath the coating. You're trying to bring together either a low alloy steel or a non-ferrous alloy, harden it, maybe apply a diffusion treatment, and then maybe have a tribological coating on top of it to get the desired nanocomposite properties from the duplex. This is something that was always the aim of Tom Bell, who was one of the earliest proponents of duplex technology, and he always said if we could possibly reach a situation where we can treat gears and bearings to give them the same capability that steels have, And we never saw it in his lifetime, but we're seeing it now. We're now seeing bearings that can perform as well as or better than steel, and these were made of titanium alloys. And we worked on a project, again together with Warwick in Cambridge, TechVac and the bearing company, together with Adrian Leyland, my colleague, and we developed a bearing, a pintle bearing, which was able to replace a steel bronze bearing in an Airbus undercarriage and take out hundreds of kilograms of weight. And that particular bearing, I'm told, I find it amazing, but I'm told that could save £7.6 million in fuel per plane over the life of each aircraft, or about 36,000 tons of CO2 for each aircraft over its lifespan, enabled due to this combination of an underlying hardening effect and an appropriate coating on top with the appropriate hardness and elasticity. Another duplex approach is to use something called plasma electrolytic oxidation. And again, we have a world leader in this technology here at the university, Alexei Yerokin, who has developed this technique, which uses a aqueous electrolyte and is better than conventional anodizing in an acidic electrolyte, better than thermal spraying in many conditions, and produces a very dense coating. And the electrolyte is non-aggressive, safe, silicates, aluminates and phosphates are used. It's ecologically friendly and inexpensive. And the process was originally developed in Russia, and one of the earlier proponents said that it can give better wear performance. You'll see here he's talking about better wear performance at lower hardness, and I'm pretty sure that's because these coatings have a high H/E, and that's why they're so good. Those coatings are now used in all kinds of applications, and especially in applications where a top coat is provided, maybe electrolysis deposited, solid gel, or organic paints. And I know that there's at least one person online who's interested in the use of paints on top of PEO treated surfaces. We know that these companies are interested in large car parts, doors and bicycle parts, and it's a process with a lot of opportunities and possibilities. I would say that it's environmentally friendly, got a lot going for it, but maybe not suitable for all tribological contacts if the contact pressure is too high. So, slightly over Alex's prediction on the time, but hopefully we've got time for some questions. We require to match the elastic properties of the coating to those of the substrate. The enhancement of those properties is best achieved through nanocomposite and nanolayered structures, and we can achieve specific functionalities such as slow release attributes as well with these nanocomposites. And if we combine those together with another treatment to get a duplex process, then we get the possibility for even better performance. Thanks very much for listening. What I've done, by the way, is I've added at the end of this a book and also some references. I'm just going to leave each of these on for a couple of seconds each, so that if you want to go to them when this is on YouTube, be able to access these papers and look at what's been done since the work that was reported here was actually completed. Okay, so those are some more recent references. Thanks very much. Any questions?
Great. Thanks.